Thanks for showing up. Hopefully you had some pizza and are feeling good. Niles, thanks for preparing this presentation. And without too much ado or hoopla, oh yes, and of course thank you to Vivint for sponsoring us with a nice place to be, protecting us from the elements, feeding us, and providing a great atmosphere and community to be part of. So thanks again to Vivint and to both Jeff, well mostly 100% Jeff tonight. So with that, Niles, go ahead and take her away, and then I'll start posting this in the Zig channel in case anybody wants to watch.
Sure. Yeah, well, thank you everybody for being here. This is Accelerating the Zig Parser Part 3. I've given 2 talks on this already here. One at the beginning of the year, and then one, I don't know, a little bit later. You don't have to have seen the first 2. I will kind of be reviewing the major thing that I presented in the first talk especially, and then in the second talk it was more like comparative assembly routines, which some people liked, but also I think some people will appreciate that we're not doing that again. What we're covering today, let's see if I can blow this one up a little bit. I'll do a little bit of compiler 101 stuff, like what does it do, just basic review, and then I made this presentation on my machine, and then I'm using a laptop that's not my machine. So yeah, we're going to review how tokenizers typically work, how my tokenizer worked from my previous talks, and then talk about entering a new era for tokenization, and then hopefully we make it into the parser proper today. I'll try not to get lost in the weeds too much. And yeah, it's not going to be on optimization fundamentals, which I talked about more in my first talk, and the comparative assembly routines are not going to be making that much of a showing today. So yeah, just basic, what is a compiler? It's just, the main thing you want to do is you want to convert some high-level code into a sequence of instructions. And you can kind of see by the example that this is kind of a complicated task. So we have a loop going on, and we're doing we're doing r and equals r minus 1, and we have types and all this stuff. And at the end of the day, we want to turn it into a very efficient routine where the machine will be able to execute a couple of instructions. LLVM can't actually do this today, but I just wanted to show this is a fun trick that is applicable to my work. This is a fun identity. Here is the internals of the Zig compiler as given in Andrew Kelly's talk, Practical DoD. I have a Vimeo link here if anyone wants to look it up later. And you can see on the upper axes we have the different stages of the pipeline. So we have a tokenizer, parser, AST-gen, we have a SEMA, phase, code gen, emit, and then on the lower axes we have the different intermediate representations. You can see a lot of them actually have IR in the name, referring to intermediate representation. The initial phases of the compiler obviously are the tokenizer and the parser, which we'll be talking about. And yeah, we take the source code, and at the end of the day we want to produce machine code. There's a few other things that a compiler does besides just this main thing, like making sure that the executable that you produce conforms to what the operating system target that you choose prescribes for an executable. So I hesitate to show this because I don't know if the sizing is going to be right, but nope.
Hit command minus a few times.
Okay.
Or control minus or whatever. Yeah, just get it to the size that fits for you.
Not really.
And maybe next time don't do this on an 8K screen.
That's fair. That's fair. Okay, so what we're doing is we are breaking up the file into pieces. So source file, source code, it's a bunch of bytes. And that, from a computer's perspective, is mostly fluff, right? The reason why we write it this way is it's nice for humans to look at, where we have these nice long identifiers, we have these keywords that are longer than a single byte, which is what the computer really would prefer. And so we just want to chunk up the file. So export is going to be its own thing, FN is going to be its own thing, column counts, and the thing that I'm talking about is a token. And yeah, so for the first 2 or 3 passes of the compiler, a lot of what we're doing is we're building up information that is, in some sense, it's already in the file, but we're just sort of compressing it so that it's easier to deal with. So that in the parser, the next phase of the compiler, we don't have to go byte by byte. And so the tokenizer's job is to make a token that says, the first box here is going to represent export. And it's going to say, where does it start? Where does it end? What's the length? We don't have to store all of those things, but fundamentally that's the information that we're looking for in this pass. And then, yeah, so we do classification of keywords. So we actually will have a kind inside of each thing. I might be able to show something here. Yeah, we have an export keyword. We say where it starts, where it ends, what's the length. And it's supposed to be changing, but it is not. But you could just imagine that it could say the kind is an identifier, or an open parentheses, or a colon, or a built-in, or a number, or an identifier for a U8, or open and close parentheses for those, and a comma. So each individual thing, each piece of the file is going to be its own token. And yeah, we'll talk more about which of these we actually want to store. You don't have to have all of them, right? Let's see what else is in store for us. Oh, okay, conventional tokenizer. We have a picture, I guess. Conventionally, how a tokenizer works at a high level, I went into this more in my first talk, but the basic idea is we're going to have some loop, and you can see we switch on the current character. That's what I use cur for. Cur starts out as a pointer to the first byte inside of the source, and then we say, okay, if it's alphabetic or an underscore, we're going to hop in here. If it's a number, we're going to do something else. If it's a quote further down here, we're going to do something else. And yeah, so the way that I want you to think about it for this talk is we switch on the first character of a token. We have a while loop where we iterate over the continuation characters of the token. And then once we're done, once we're done matching, in this case, alphanumeric or underscore characters, we break out, we write it to the token buffer, and then we go back to the start and we start matching more tokens. So it's pretty simple. There are other ways of doing it, like a DFA way, and I went over that more in my first talk, but this jives nicely with how I want to explain what the improvement is. So we're just going to go with just this for today. My tokenizer, this is sort of what I wanted it to look like. What we do is we produce a number of bit strings for each chunk. This is the tokenizer I presented at the beginning of this year. And so for every 64-byte chunk, we can produce 64 bits. Now the reason why I chose 64 is because the machine can efficiently operate on 64-bit integers, right? And this is true, even if you're on a more limited machine that doesn't have SIMD, doesn't have bit manipulation tricks. And I went over this more in my previous talk, how you can do this on this RISC-V single board computer that I bought, where it doesn't have nice SIMD, it doesn't have nice bit manipulation facilities provided. And yet you can still use this technique and you can still get very nice gains from it. So the idea is we produce these bit strings and we can use it to jump ahead in tokenization. So we still switch on the first character of each token, but we look at in the bit string to help us. So this first bit string tells us where the alphanumeric or underscore characters. The second one tells us where the white space characters, which for this particular chunk is not that useful, but you can imagine at the end of this line, there's going to be a new line, there's going to be some number of spaces. And when we switch on the first character, the next thing that we do is we query the bit string and we say, how many ones start at that position? And we can do that in like 3 cycles or 4 cycles. And this enables us to jump to the end of a token without having to branch on each character. We don't have to have that while loop where we're going character by character now. So the only time that we would actually branch for this is if we actually ran off the end of the chunk. I might be able to zoom out a little bit here, or a lot. But yeah, so we can just sort of jump. You can see that with some of them, they're only 1 or 2 characters, and so it's not always helpful for that in the sense of jumping over multiple characters at once. But it's still helpful in the sense of we have eliminated branching, okay? Because how a typical tokenizer works, like I showed, is we switch on the first character of a token, and then we match the continuation characters. So what that means is that the CPU, when it's doing branch prediction, fundamentally is trying to guess, like, how long is this while loop going to go? Therefore, it's basically guessing how long is each identifier based off the previous one. Identifier or keyword or number. They're all in the same category for in the code. And you could probably tell by looking at it that this is actually an impossible task. The CPU's branch predictor could not predict, based off of the code that came before, how long the next thing will be. And so alleviating this need to actually predict how long the next token is can get us performance gains. Let's see what else we got. Okay, so yeah, I just linked this. Do you have a question?
What did the third row represent?
Yeah, okay, the third row actually represented new lines, which we have 0 here. And yeah, actually control characters in general. And what we use this for primarily, although I didn't need to show it on this slide, what we would use that bit string for is if there's a comment, we can jump to the end of the line. And same thing if there's a line string. In Zig, we have the double backslash, and that you go to the end of the line. You can have more than a single line with this if you have double backslash again. But luckily in Zig, you do have this nice property where there's no token that can go over a new line. So you don't have like the /* multi-line comments. If you want multi-line comments, you have to have a double slash every line, right? So
The way the good Lord intended.
there you go.
Quick question. So to
Yeah.
create that 64-bit integer, you still had to run through the bytes individually.
No, because we can do this in SIMD, and this is what I went over a lot more in my previous talks.
Okay.
But basically what we do, first of all, modern CPUs provide us with facilities to do precisely this. And actually, if I show you the code here, which is the next thing.
What, real quick,
Oh,
what
I
was
know.
the intent when they provided us with this? Like, was this intended to make audio encoding or decoding easier, or like there must have been a specific reason why these features exist that is not text box?
No, about SIMD, right?
I don't know what I'm doing.
Well, look.
Not at that level.
Okay, so SIMD, what it's for is being able to operate on larger amounts of data at once. And it is another dimension in which we can get at parallelism, data level parallelism. So when you have any scenario where you can where you can operate on chunks of things at once, you can do better. Is there any way I can get on the internet here real quick?
Yeah,
Yes.
it's VisitorNet.
I don't even know where to find the thing on this computer screen. Okay, here we go. Visitor
They'll
net.
change the icon on you based on the state of the connection.
And then we have
The password is
should I take a picture?
Shown on that paper?
gosh dang it.
It might be able to scan it. Can you flatten that for me? It just says visitor net. Or maybe it does have a password, but it just
Let me
not
go
showing it.
ask Pool.
I'm pretty sure it has a password, but I can't recall what it is.
So are these the same instructions that you would use for like image manipulation instead of going byte through byte in a
Yeah.
traditional sense?
It-
You have, or a 64-bit, like you have your bus, 64-bit bus, you can do 108 instead or whatever, or groups of like 10 8-bits or whatever.
There it is.
Yeah.
Oh, guess you got it.
Energy guest bang bang. Ah, there is one. Okay, I'll remember to take
Sorry,
that one
the
back.
pencil was.
Okay, getting redirected. Here we go. I will not do anything that you guys don't like. That's that terrible.
You can do stuff energy doesn't like. That's fine with me.
Okay. You're
What
true,
if they
true to the
don't
roots,
I
not
work
true
for
to the...
Vivid.
Yeah. That's funny. So here's my tokenizer. And yeah, you can see in Zig, let me see if I can blow this up a little bit. So what we're doing, this is obviously somewhat simplified because in my real code, I actually put in platform-specific optimizations to make sure that the compiler actually gives me the emit that I want for certain things. For example, if you go on ARM, the emit is not like perfect, and I really wanted to like kind of push the boundary and see what we can do. But yeah, so in terms of people asking like what was SIMD designed for, like why does it exist? It's another avenue in which you can access parallelism in your program, where you can do more than one thing at once. And so, you know, we have things like this where, you know, for example, the bit manipulation things, that's probably the earliest version of data level parallelism that we have. But really, like anytime you're dealing with groups of data at once, it comes up in video games, it comes up in, you know, encoding stuff, encoding things, where yeah, anytime you want to grab, you know, 8 U64s at once and do some calculation on all 8 of them at once, that's going to be faster than just doing the calculation on one of them at once. And when it comes to your question about are we going one by one, we are not. So we are doing this in SIMD. What we're doing is we're checking, yeah, this is the control characters bit string, the white space bit string, and this produces the bit string for underscore, lowercase alphabetic, uppercase alphabetic, and number. So this is...
So we're still going through the byte string. We're not going one by one though. We're using SIMD to pack them together, and we're creating this 64-bit integer
Yeah.
So
with
you're
SIMD. Okay.
You're not even dropping down into assembly to do this. This is...
No, I'm not handwriting assembly. There are some times in my real code where I will put like an intrinsic when the compiler doesn't know how to do certain things. And yeah, if you look at LLVM project, sorry, this isn't my computer. So if we look at author valid arc here, you can see I've noticed a lot of instances where the compiler sort of messes something up, and I'll probably come back to one of these. But if we just want to look at one, this is ARCH64, just so I can show you basically what I'm talking about here. Okay, let's just open it up. I can do this. I can type it just really quickly, just so we can see. So if we open up Godbolt, I don't know if you guys have ever used this.
We've been on some Godbolt.
Okay.
What?
What's going
I think
on?
it's Godbolt.org.
Oh, godbolt.org. Let's do that. And if you use the zig.1, I think it'll open it right up to zig.
I did not know that in the book.
There we go. Okay, so yeah, let's get the zig trunk. And you can see this is how it compiles and multiply in debug mode. So if we do /o release fast, let's do that. Then this will optimize it. And it will optimize it for actually whatever computer it's compiling on in the cloud. And so we can actually do target, I think, x86, 64, Linux. I think that's the right order. Usually I don't even have to type this. So Zen 4, if it worked. There you go. Okay, so if you want to do stuff in SIMD, let's load in a vector of 64 U8s. And then let's return a U64. And we can say, let's just say this is our chunk. And we do chunk equals, what do you want? Spaces. Let's do spaces. And right now, Zig did not add all of the features that they're planning on with type inference, so you have to actually put an as in here to say what type it is. That's something that's gotten interest like last week, where they're like actually talking about, you know, making this easier so you don't have to say each individual thing. And yeah, so first of all, you can see that this returns a vector of 64 bools, and so we can just bitcast it to a U64. And what this will give you is some SIMD instruction here. So let's turn the output up a little bit. And this is a vector packed compare equal with byte granularity. That's what that means. And you can see we're loading in this ZMM word pointer. That means a 64-byte pointer. And this is a relative instruction pointer plus this label, which just means load the data that's this right here. So this is 32, which is your space character. And it's gonna compare 64 spaces up against whatever's in your input chunk, which is ZMM0. And then it's gonna stuff it into K0. And K0 is, this is actually a new register file for AVX512. Zen 4 supports that. And yeah, so it will give you 64 bits, and each bit will say, it'll be a 1 if it was a space in the position, and it will be a 0 otherwise. Does that make sense, what I'm talking about? So it's like, let's see, can I hit F12? There we go.
So you have 64 bytes.
Yeah.
How many registers are you packing them into for the SIMD?
Well, if you have support for 64-byte vectors in this instruction set, this is all in a single vector register.
Really? Okay.
ZMM0 is the one vector, that's your input. And then this one right here is implicitly loading it into a ZMM vector, of which there are 32. And yeah, and then this will put it in this bit string, and then we can move this over to a general purpose register, and there you go. We have 64 bits of information of where did it match. And so you can visualize it like this. If I have some characters here, and I'm not going to type spaces because you won't see it, but you could imagine if you line this up, okay, what it's doing is it's doing a compare equal in each column. So it's saying, is this D equal to this value in this column? And so it's a very simple routine here. And yeah, this works across machines. You can switch to Zen 3, for example, where we don't have AVX512. We only have 32-byte vectors on that machine. And it will compile down. This is some C ABI stuff, so just ignore that. It wouldn't show up in your real code unless you were exporting it to C. And yeah, so you load up this byte pointer, which is still your space, into YMM0. And then this is actually pulling in your input. Again, this is C ABI stuff. Normally it would just be already in a vector. But yeah, and then we can do, YMM0 compared to your data, YMM0 compared to your data. And this will actually produce 32 bytes, and each byte will be all ones if it was true, all zeros if it was false. And then you use this move mask instruction to take it from a vector into a general purpose register, and it will actually grab the uppermost bit of each byte and concentrate it into 32 bits, shift one of them to the left by 32, or them together, 64 bits. There you go.
So on that newer CPU, you actually have 512 bits in a single SIMD register.
Yep.
Dang.
So on Zen 4, it's actually double pumped, which means in the microarchitecture, it only has 32-byte vectors. It only has 256 wires, and so in order to give you the answer of 64-byte vector operations, it has to run it through twice, basically. Which is why if you upgrade to Zen 5, which has gotten sort of negative press for its performance implications, it's about 2 times faster on AVX512 workloads because it actually has 64 bytes. It actually has 512 wires everywhere in the microarchitecture. And so the instructions are fully wired up for 512 bits. And yeah, so you can do this all. And you'll notice there's also no branching here, which is something that we wanted to eliminate.
And are these specialized vector registers, or are they also used for floating point?
Yeah, there are floating point vectors. I have not really touched those, but you can type it in right here. You could say F32.
Oh, like you're actually vectorizing the floats.
And you're not going to fit 64 in a single one, but yeah, let's say on Zen 3 we have 32 bytes. So let's say 32 divided by 4, let's say 8. And then let's do, let's load 2 of them in. And yeah, you can do this sometimes. If you don't know if a machine can do something, if you trust the compiler to know whether it's possible, you can just ask the compiler this way. You say, can I add things in SIMD like this? I want to add 8 floating point values, and there you go.
Wow.
One instruction.
Wow.
And yeah, so you can do a lot of things with this. And this alleviates the need from like needing to have an independent instruction for each of those things, right? And so yeah, if you had a machine that didn't have any SIMD, like I have that RISC-V 64, I think that's how you do it. And then it's called the Sci-5 U74. Yeah. So you don't have SIMD on this machine. And so it's going
So
to
you're
be,
literally just doing 8 floating point
yep,
operations.
it's going to be one by one.
Well, that's super cool. My question was if on the other architecture, if those registers are also used for just regular old floating point.
Yeah, they are.
They are, okay.
If you do, yeah, if you just
Like
do
the YMM
a single
0.
F32,
It'll still use those registers.
yep.
Oh, using the XMMs. Interesting.
Yeah, so XMM means 16 byte. So a little bit of history for anyone who's interested. MM was the original one. I believe it was 8 bytes. And it was part of the multimedia extension. XMM was added as extended multimedia. And then YMM and ZMM came after that as extensions to that. So we went from 8 bytes to 16 and 32 and 64. And it works like other registers if you're aware of how it is, where they didn't just like add completely new registers, they extended the existing ones. So you saw this historically with, you have your 16-bit register, and the 32-bit register is a superset of it. And the 64-bit register is a superset of that. And in SIMD, you started with 8-byte registers, which you don't, the compiler will not admit it, you wouldn't want to use the instructions for it. But the XMM is an extension of that, 16 bytes. YMM is an extension on that. And so yeah, you can sort of mix and match these two, where if you do some calculation where you say, okay, well I know from this 32-byte operation, I'm going to get something out that's just 16 bytes that I care about, then you can just like go down to using X00, and it'll just use the first half of Y00. So, and the compiler will manage this for you. So, yeah, fun facts.
Very cool. I'm sorry if I'm going on the weeds.
That's
here.
fine.
This-
But yeah, and so you can see we produce the bit strings, and then we figure out what is the current misalignment. That's what I call it. So the cur.pointer, that's where we are in the file, and yeah, I turn that into an integer and I truncate it to the log2int of a u size. So how big do you think that is?
That's a type.
This is a type. It's,
Logged in of a U size.
yeah, Zig you can call a function at compile time, and types are first class values at compile time.
You're calling a comp time function to get the type.
Exactly.
Gotcha.
So do you know what this evaluates to? For a 64-bit machine, it will be the log2 of 64.
64 is 8, right?
6.
No. Yeah.
What?
6. 2 to the 6 is 64.
2, 4, 8.
Oh.
16, 13.
All right, yes, not
Yeah.
square root.
So, so yeah, so what this is doing, it's going to take the lower 6 bits of the pointer, and then it's going to shift whatever bitmap we picked by that amount. We do a not, and we do a count trailing 0. So that's what I was showing over here, where we were jumping ahead with this iterator. Where we're doing this query, we say how many ones start at this position. So one thing to keep in mind is on a little endian machine, when we load this in a vector, the bytes that you're seeing are kind of going to be the other way. Now, it's actually better that this is the case if you've worked in this. You realize that. But when it comes to depicting it in a talk, it's a little bit more cumbersome. But yeah, so actually on the left-hand side of the bit string is the trailing end. So when we say count trailing zeros, we're counting this way. And when we say shift right, we're talking about left visually. So you could say this is kind of like a big endian depiction. On a big endian machine, this is how it would work, and we would use count leading 0 and shift left to accomplish this. The reason why we do a not and we can't like factor that out is because when we shift the bit string, it's going to shift in zeros. And if you have an instruction that's counting zeros, you don't want it to count things that are not the bits of information, but instead padding, fluff, right? And so that's why you have to do it this way. You have to shift it and then do a not. So the stuff that's shifted in will become ones, and therefore you will not be counting bits that are not bits of information. So, fun fact on that. I don't know how long this goes. Okay, so that's the code. Okay, so I argue that tokenization is akin to the problem of bits to indices. So that's where you have some bit string. Let's see if it'll do this. You have some bit string, and there's ones somewhere. And you want to produce an output buffer that tells you at what index these ones exist. So I have here that there's in the 0 position, there's a 1. In the 3 position, there's a 1. 4, 7, 8, 9, 10. I had to use single letters just because I want it to line up on a monospace font.
So are you parsing left to right or right to left?
Left to right in my depiction.
But in actuality?
In actuality, when...
Because you're more efficient right to left, right?
If we're talking about, like, in terms of a source file, I load the first 64 bytes first. If we're talking in terms of, like, little endian, it is sort of like it's flipped around from how I'm showing it.
Okay.
So yeah, everything here would be reversed. Everything on this slide. But in terms of, like, the source file, you're still looking at the first piece of it first. But it's just like in the CPU, it's backwards, at least according to how I'm observing it. I don't know if they actually flip it the other way inside, but.
So because, like, when you're like parsing the other way from the end of the line to the beginning of the line, you always know that something exists at the beginning, right? So well, go ahead.
Yeah, I guess I don't know what you mean. Okay, so bits to indices. How would you solve that? The naive way, I'm giving the game away a little bit here. You could go bit by bit. You could go 1 bit at a time, and you just have a loop. I'm sure you guys would all know how to write that loop. So I didn't show it. But yeah, you would say while true do, have a bit shift to isolate each individual bit, or you could even use, like, a fancy language feature in Zig, where you're like, oh, bit cast it to, like, an array of U1s or something, and then, like, just give me each U1. You could do something like that. But yeah, so the amount of work and the number of branches is proportional to how many bits there are for this solution. And this is sort of like what most people do for tokenization, is they're going byte by byte, and they have a switch statement that's switching on the first character of each token, and then they have a while loop, which is matching on each continuation character. And so sort of, so I argue that bits to indices is like a simplified version of the tokenization problem. And the second way to solve this is to use a heat-seeking strategy. So this is basically like what my tokenizer that I presented at the beginning of the year does. So how we would solve this with a heat-seeking strategy is we would say, count trailing zeros on the bit string. The first answer would be 0, because it's in the 0th position. And then we can unset the lowest bit. There's an instruction to do this, and you can just say, okay, for bit string x, x minus 1. What minus 1 does at a binary level, you could think of it like a loop. When we subtract 1, we're flipping the trailing zeros, and then the lowest 1 bit, if one exists, will be flipped to a 0. And then we can say, take that value, that's x minus 1, and AND it with x. And so what we did is, the critical thing here is that we flipped the lowest 1 bit. And so when we do x ANDed with, let me put this in my pocket for a second. When we say x ANDed with x minus 1, in Zig we like to write it like this to show that it's fine if it overflows. And yeah, so this means if we have some zeros and a 1, or maybe it starts with a 1, let's say. If we were subtracting 1 from this, which again I'm writing it backwards, okay, we're going to be looking at, we're going to be flipping each of these ones, each of these to 1s, and then the lowest 1 bit will turn to a 0. Everything else will be the same. And yeah, I apologize if that's confusing because it's backwards from how numbers typically are. But you could write it the other way. So if you had like that, and you subtracted 1, right? It's like, okay, carry, 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 right? Right? That's what I'm talking about. So this bit flips. So that's why this deletes the lowest 1 bit for x. Okay. So for this strategy, the amount of work is proportional to how many 1 bits there are. Now our loop is not, it doesn't necessarily have to go 64 times if we have 64 bits. Instead, we say count trailing 0. The first one is at 0. We unset it using that trick. And then we do count trailing 0 again. So this will be a 0. And when we count trailing 0 at that point, it will be 3. So we'll get 3. And we unset that. And then we count trailing 0 again. We get 4. And we keep going until we run out of 1 bits. So this is going to be more efficient if the number of 1 bits is less than the number of total bits. And when it comes to the tokenization problem, what we're using this for is jumping over the continuation characters of a token. And so, roughly speaking, this means that we experience a reduction from the amount of work that we're doing being proportional to the number of bytes to roughly being proportional to the number of tokens. Now, you could technically, theoretically, you could have like a gigabyte full of zeros, and when you do count trailing 0, it will not take you to the end. So it's not technically true that the amount of work we're doing is directly proportional to the number of tokens, but that's sort of correct in practice, and it's the right way to think about it. And there is a way that you could do better than this as well. But the reason why I chose to implement it this way and present on it earlier this year is because I knew that this would be a good strategy across hardware, across architectures. And yeah, so I showed, I forgot this isn't my computer, so it doesn't have my history. So yeah, on my GitHub here I have this project. And these are the measurements from earlier in the year. At that time, the mainline Zig tokenizer was slower, but it would get about 250 megabytes per second. And my version got 753 megabytes per second, so it was roughly 3 times faster. This was with the UTF-8 validator turned off. When I put it back in later, I didn't update this, it was 2.75 times faster. Now recently, Zig had an update to the language where we finally got labeled continue statements. So this enables you to have effectively go-to, but without the problems of go-to where you have like uninitialized variables and this sort of thing. So instead you have switch cases, and you can say continue to that switch case. Jump directly to the logic that I want. And so you can actually have any control flow that you want to express is now expressible in Zig without tail call functions, which would be the other way to do it, but it makes your code really unreadable if you have a lot of variables you want to pass around. So yeah, and yeah, this is good across architectures. So on the Sci-Fi U74, it was about 2.5 times faster. Again, I didn't update it with the UTF-8 validator. I actually don't remember how much of a pessimization we would get, but I also have had some more optimizations I talked about in my last talk for this one, like the count trailing 1's digression that we went down last time. So anyways, that's why I went down that rabbit hole. But there's this one video I want to show, like the first 15 seconds of it. I'm going to see if I can just make sure I know what it's called on my phone first. Yeah, okay. It's YouTube.
By the way, about 10 minutes ago, Caleb said hi.
What's up, Caleb? Okay. I believe it was Optimizing with Bad Code by Case Iminar. So yeah, I watched some of these Mario 64 videos. Mario 64 is actually like a field of science. That's not even a joke. I don't know if you guys have ever seen it, but there are parallel universes. There are people who study like how the walls work and people who study the different tricks. And then you have, it's also a sport, you know, because you have speedrunners and then you have people who like have insane input abilities, and yeah, it's actually like a field of science. It's and it's also a sport. It's very interesting, and there's also programming content for it too. So yeah, will I be able to play this and get audio?
I guess we can find out.
Let me see if my
It's also a field of science because they released it with debug symbols.
yes. So I could do it from my computer, or I could do it into the Intel one there. Is one of those hooked up to the audio or no? Probably not. I could just do it from my computer, but
That's fine.
yeah, let's just go for it.
Programmers have a lot of guidelines to determine what makes good code. The goal here is pretty simple. We want code to be performant, we want it to be readable, and we want it to be easy to upgrade. To achieve those three qualities, programmers have built a lot of principles for how to write code. And I would argue these principles make sense most of the time. But what happens if we sacrifice every principle for the sake of performance? When we say skill issue to anyone who can't understand the code, and when we don't mind turning our code into an absolute abomination that only works on a single architecture and is near impossible to debug.
Isn't that just called assembly?
Well,
Let me put it this way. There are techniques that the average person would not be able to maintain your code if you did them. And we're going to go into that.
The average person cannot maintain code.
Fair.
The average code cannot be maintained.
Also fair. All right. Third strategy. Vector compression. This is the secret sauce. This is the secret formula right here. This is a new, a new strategy that we can use for tokenization, and the nut has not really been cracked on this before. Some people have. There was a guy in the Zig community actually who did a master's thesis on parsing on a GPU, and some people have sort of done things that sound like they might be similar. I'm not sure, but in terms of parsing an actual programming language, this is something I don't think has really been done before. We do have example of like SIMD JSON, for example, which obviously I studied that in order to get the skills to do this. But that's not a real programming language, and a real programming language is a little harder because we have comments and we have a bunch of different operators and keywords and a whole bunch of fun stuff. So with vector compression, the amount of work that we do is proportional to how many chunks there are. So why is that? It was actually this animation that I showed here. Let's see if I can blow it up a little bit. So what we can do is we can make a vector that has every index counting from 0 to 64, sorry, 0 to 63 inclusive, inside of a 64-byte vector. Okay? So you can just imagine that I didn't put the letters there, but it's actually saying 10, and it's actually saying 11, 12, 13, 14, 15, all the way up to 63. And when we produce some bit string that has the information that we want, we can use a vector compression, which looks like this. Okay? And that can compress the information that we're interested in into the front of the vector. So what this is useful for, so I say we have VP compress B on AVX 512 machines. So what this means is it will take in a vector, it will take in a bit mask, and then we can make the vector counting from 0 to 63, and VP compress B will return back to us a vector that says, okay, there's a bit at this index, this index, this index, this index, and that index, right? So we can use this for the things that we care about. We can produce bit strings for all relevant information. We operate entirely on bit strings until we produce a bit string that says, where does each token start? Where does each token end? And that's not even close to how it's supposed to look. Okay. Sadness. All right, so the point is, I dropped my recorder here. Hopefully it's still going.
This is still going?
Yep. All right. So let's say we have export fn foo, and then we have some vec, because I like vectors. Okay. And yeah, I can keep writing it, but this is the point. So we're going to produce a bit string that tells us where do they start. And starts right here, starts right here, starts right here. And everything else will be zeros. Apologize that this is not monospace.
Yeah, that's going to be a problem.
It doesn't matter actually, but it's just like it's just we're just marking where does each one start. And yes, we have padding in here, and then there's a space in here, and then we have stuff that's not the start. Is that the right number? Okay. And then we produce a bit string that tells us where does it end. Okay, right here, right here, right here, right here, and right here, right here, and right here with the R. Okay. So what we do is when we have a vector that counts from 0 to 63, right? 2, 1, 2. Okay. Point is, using a vector compression, we can isolate the indices that we care about all at once in parallel. So I still should be able to show this. If I scroll down maybe. It's really messed up. The point is, we care, it starts right here at 0. It starts right here at, I'm just going to guess that's 8. And then right here at 11 or something. Okay. Probably wrong. I didn't bother counting. But then if we, then when we look at the end positions, right, we have like 5, 0, 1, 2. Yep, we have 5. Oh yeah, I have it right here. So yeah, we care about the starts. We have 0, 7, let's say 10, and then 13 and 14. So if I write that out, we have 0, 7, 10, 13, and 14. Now, if I look at where does it end? It ends at 5, it ends at 8, and 12, and 13, and 16. And I left out that one. But the point is, you can subtract the top one from the bottom one and add 1, and this will tell you the length of all the tokens simultaneously for a full 64-byte chunk, fully in parallel. And so yeah, this VP compress B instruction on Zen 4 it runs in 9 cycles, the variation that we care about, and then on Zen 5 it runs in 5 cycles. And so using this compression facility, what we want to do is we want to produce for the tokens. For mine, it's a kind. It's 1 byte. Under the hood, it's a U8. We actually have an enum, obviously. And then we have a length, which is also a U8. If we need more than a U8, we're going to put a 0 in here, and then the next 4 bytes will be the true length. We cap it to be U32 because Zig makes an arbitrary limitation where we say we're not going to parse anything over 4 gigabytes. Therefore, we can always index into the file using only a U32. But in our case, almost every token you'll ever see fits within, it's going to be 55 characters or less. But yeah, if we absolutely need to, we can use up the extra space. We almost never need to. And so we actually can do tokens in just 2 bytes. What this does is it does regress the usage of it theoretically, because theoretically if you looked at a token that's in the middle, you don't know where it is. You have to look at each token in order, and you have to have a cursor into the file, and you have to add the length of each token as you go, saying, okay, we went 20 characters ahead now. Now we went 5 characters ahead. Now this also means that you have to put the space and the comments somewhere. They could be in tokens, but this is one thing where in the mainline Zig tokenizer as it stands right now, they do not put it in the tokens. They just have it erased. And the way they do it is they actually use a start index that's 4 bytes. And they actually use a multi-array list, which what that means is that they store the 4 bytes separately from the kind byte. And so in memory it would look like this. Let's say. So these would represent the start index, and then these would represent the kinds. And that's how the mainline implementation works. So these would be U8s, these would be U32s. And yeah, but we can reduce the memory consumption by doing lengths. Now, we don't actually need to store the space and the comments if we can just put it in the length of an adjacent token. So there are certain tokens where we actually don't care about the length is in terms of like, we don't have to look at the content of the token. For example, if the kind is const, or if, or fn, or plus equals, or
Export.
yeah, XOR. Anything that is a constant amount of characters, or just in fact, we're not looking at this in terms of like, what does this contain? Because all the information about what it contains is in the kind. It's only things that are variable length, like identifiers, where we want to know like what name is it. We're going to want to use that later. If it's a string, obviously we're going to be using the string. If it's a number, that's actual data, we're going to want to use that later. So we don't want to necessarily put comments in that unless we wanted to retokenize it. How Zig actually does it is they actually will retokenize things because they only store the start index, they don't store the length. And so that means that when it comes to identifiers and strings, they actually will retokenize it when they use it later. That's a trade-off they make, but I think that it makes more sense to not do that because you actually don't want to retokenize the things that I mentioned that are variable length. This looks like one of those memes. Okay. So that's sort of what a compression looks like. I mean, I drew it out. Let's see. So yeah, my design is what I said. We produce a bit string that tells us where does the token start. Produce a bit string that tells us where does each token end. And then we do a compression. We can do a subtraction and a +1. We can actually fold the +1 by making this count from not 0 through 63, but instead 1 through 64. So we can do that little micro optimization here. And then we also want to produce a vector of the kinds. So how do we do that? Well, basically, we're figuring out where each different kind exists independently using bit manipulation techniques. And then we do what's called a masked broadcast operation. So what that means is in my code, I'm going to say, let's erase this real quick. I'm going to say, okay, I figured out where the alphanumeric underscore characters are, right? It's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. There's going to be zeros everywhere else, okay? And basically, I can figure out where the groups of 1 bits start very easily. Now, in big endian masks, okay, we can say, if I shift it to the right by 1, and I do a not, what I'm tracking is where are the transitions from a 0 to a 1. That's what I'm asking. So we can see we go from 0 to a 1 right here, a 0 from a 1 to right here, a 0 from a 1 right here, a 0 from a 0 to a 1 right here. And actually at the boundary condition, right, we shift in a 0 and then we get a 1. So we can tell that this starts in this position using this trick, right? We can say x, shift to the right by 1, not, ended with x. So we're tracking where are the starts of alphanumeric underscore characters. And yeah, so hopefully I don't have to draw out what the answer was. But yeah, it starts at E, starts at F, starts at F, the V, and that V. And then you can do the same thing the other way. You can say, where does it end? R, O, N, T. Anywhere where there's a 0 going to a 1. Again, this is big ending, so in actuality you flip this around. But that's the idea, and we can do this for everything. We can do this for everything. And so that tells us where does it start, where does it end. We do a compression, do a subtraction, add 1, and that will give us the length of all tokens for a 64-byte chunk, branchlessly, in parallel. And to get the kind, what we do is we take this bit string that we produced here, the one that told us where do they start, and we do a broadcast operation. Broadcast means that we're going to take some byte. In this case, it's going to be the enum that's a U8 under the hood, the enum that tells us that it is the kind, which is an identifier. Now, in this case, we are going to have to check where the keywords are. And maybe I'll show that later if we have time, but I feel like we're going to run out. So, but yeah, so what we can do is we can just do a broadcast conditionally. So we're going to have, in my code, what it looks like, I have an older version of my code. Am I able to get out of full screen now? There we go. So I have a version of my code right here. Let's go to the first page. Not this one.
Are you going back to the whiteboard?
In a second.
I won't change that.
Hold on, I'm thinking. This one. Okay. This has a little bit older version of my code when I was working on this like a week or two ago, whatever it said when I did this. And yeah, so if we go to fn, tokenize with compress, obviously there's some debug printing going on here, and then some garbage that is deleted. We don't need that. Okay, so you can see we figure out like where the new lines, carriage returns, tabs, right? We check, is there a location where we have a new line that, or we have a carriage return and there's no new line after, we can error on that. Okay, and here's sort of the thing I'm talking about. Where do the comments start? Where do the lines start? Okay, so what I wanted to show is the kinds equal section. So that was what I was trying to get to. So this is how I had it written before. I actually changed this. But the idea, if we go look at the assembly here, you can see it as well, maybe. The idea with this is we're doing this select on each mask that's in here, and then we are doing a splat on the tag, and yeah, so we're saying when it's true, when a particular bit in mask is a 1, we're going to take whatever is this tag that we care about. So in this case, we can look at the quotes, and then we're going to broadcast the string kind into all the places in the vector that correspond to a 1 bit in here. Otherwise, we fall back on whatever it was before. We fall back on kinds. And then we do the same thing for character literals. And so we broadcast that byte. And yeah, so we always fall back. In assembly, let's see if we can see it here. So it's not using the broadcast. Maybe it should. But what it's actually doing is just loading up a full vector of this byte. So this is an enum, and it's a U8 under the hood. And yeah, so it's going to take this enum, and it's going to move it into kinds. This is the kinds vector here, based off of what's in K2. This is our mask. You can see that the code that the compiler generates is absolute not good stuff. You can see that it's like moving from a general purpose register to K1, and then we move from K1 to the stack, and then we move from the stack to K2. So this is why I submitted this bug to LLVM. They don't compile that well for AVX 512 yet. Register allocation is a work in progress, I guess, for AVX 512. Yeah, this is obviously bad. Obviously, you would just move from RCX to K2. You don't need 3 instructions, and you don't need to go to the stack. But yeah, the principle is the same. We can move certain values conditionally into ZMM19. And so And so yeah, so we're gonna have a vector, and let's just say it starts empty, and then let's say I figure out, oh yeah, the starts are right here, and so I'm gonna say identifier, 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 identifier. And then next time I'm gonna say, well, what about this symbol? I'm gonna say, I actually just say symbol, 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 and then we have another symbol over here, obviously. And so yeah, we can do a masked broadcast, and we can assemble a vector of 64 bytes, and it will contain the kind of each token at the position in which it starts. And then at the end, we do a compression with a bit string that tells us where do they all start. And that will give us a vector which tells us what is the kind of every single token in a 64-byte chunk at once. And then we interlace them, which we have a way of doing that. And so it will take one from kind, one from length, one from kind, one from length, one from kind, one from length. And so at the end, you're going to have up to 64 of these written out for a 64-byte chunk, almost completely branchlessly. Now, yeah, you can see that this code, go ahead.
So you mentioned how the current tokenizer holds on to the start, does not hold on to the length. And I saw the presentation of why he does that.
Right.
You think that we should contain the length. Are you including the start in the final token? You just have the kind and the length.
Exactly.
Okay.
So yeah, we don't have the start index. So that means that in order to go over the tokens, you have to have a cursor into the file, and you have to add the length as you go.
I see.
That way you know
So you're
I'm starting here when you're actually using it, and then you say, okay, I'm starting here, I know the length.
So does that remove the ability for kind of random access?
It does.
Okay. You have to traverse it.
Yep.
Gotcha.
You could do a scheme which is used in some other subfields of computer science where they're like, oh, well, we're going to divide this by log n by 2, and every interval of that, we're going to say, like, here's the number of characters up to this point. And then you can guarantee that within a certain amount of time, you can actually just you can do sort of random access, like to an extent where you're going to get close enough, and then you'll have to add the last couple ones, right? And so you could guarantee that it will work in logarithmic time, or whatever it is for your trade-off that you're doing.
Gotcha. Interesting.
But yeah, this does pessimize that. However, within a compiler, we're always looking at everything. And this is something that I thought to myself a lot when I was working on a TypeScript to Lua transpiler, where I'm like, we're iterating over this tree every time in the same order. We're not skipping any of it. Why don't we just have a flat array that's exactly in the order that I want it, produced efficiently if possible? Why don't we just do it that way? Because we're not actually using the theoretical advantage that gives you. We're not actually using the ability to access something completely randomly in practice. Now, yeah, and if you were talking about well, how do we throw errors if we want to collect a bunch of errors and then throw them? Well, I actually don't think it's that bad to just you could say which token it is. You could just iterate over the tokens again and just say, oh yeah, here, 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 and here. That's not that bad. I mean, it's only 2 bytes per token, and it's smaller than the size of your file by a lot, actually. I actually have it here for the benchmark where I downloaded 59 megabytes worth of Zig code, and for my implementation it was 18.5 megabytes of tokens. So that represents a dramatic reduction over the source file, and so I think sort of optimizing for that is not really helpful. Also, it's an error condition. So what we really care about is when someone downloads code and they're doing a cold compile, they don't want it to take 10 minutes. So I think we should optimize for that as opposed to error conditions. But even still, the error condition will be perfectly fine. So yeah.
So by the time when you're actually in practice, you have your tokens, and you need to put Okay, well, say you need to actually know what the identifier is, for example. At some point later in the stage, you have your tokens. By the time you get to that identifier, you already have an index into your source, right, is the idea. And so if you need that string of the identifier, you're already there. You don't have to like random access to it.
Exactly, that's what I'm saying. Yep, cool. And yep, that's the plan. So there's a problem with this. Like we have to deal with strings and comments, right? Data could be inside of a string or a comment, and we don't want to tokenize it individually, right? If this whole thing was inside of a string, it wouldn't make sense to say, oh, an identifier starts here, but it's actually part of a built-in. Oh, these keywords are here. We wouldn't actually want to identify that, because that's not how it actually works. And so, I don't know if this will work. Yeah, the other problem is strings can be inside of comments, and comments can be inside of strings. What I just mean by that is you can have an arbitrary assortment of double slashes and quotes, and if you just looked at the end, you wouldn't be able to tell me what you're inside of. Now, there is some parallelism here inherent to the Zig programming language, which, like I said, tokens don't go across new lines. So anytime there's a new line, it's a context reset. We know for a fact we're not in a comment or a string or anything. So we do have some inherent parallelism available to us. And yeah, so you could have this. It's probably not going to show anything, right? But, okay, I can make it small. And yeah, so the point is, what we want to do is we actually make an iterator after each new line and then also at the start. So we have an iterator here, here, and we would have one at the end here for the next thing. And I didn't like count this out as 64 bytes or anything, but the idea is we can deal with strings and comments in this way by doing a subtraction. Okay, so we take this bit string and we subtract it from the OR of these two things, and also two more. So we have a bit string that tells us where are the unescaped quotes, and we actually can produce that in parallel as well using something that was developed by John Kaiser for SIMD JSON, where we can actually tell very efficiently using bit manipulation techniques where are the even or odd backslashes. We care about the unescaped quotes. So if there's an odd number of backslashes before a quote, that's considered escaped, and so we don't care about it because it cannot start or end a quote. So therefore we just ignore it off the top. And we can do that context free, because if it's in a comment, it doesn't matter. We're just talking about ignoring something, so it would be double ignored, I guess. Okay, so yeah, the point is we have this iterator, and we're going to take the OR of the things we care about. Where are the unescaped quotes? Where are the beginnings of the comments? The beginnings of the line strings, which would be the double backslash. And then we do a subtraction. And the subtraction is what I was talking about earlier, where we do, where we can do x minus 1 ANDed with x. To unset the lowest bit, we're doing the same trick here, but with multiple bits in parallel, because we know that there's going to be some boundary here, if not there being a new line. And so we actually OR the new line in there as well, so that we know we're going to stop on something. We're not going to just run off into the next chunk and screw up our data. But yeah, we can do a subtraction, and we do the same trick. Take the not, do an and what this will do is this will make it so each one of these bits is like a forward iterator. So we can tell, oh, go to the next one bit, go to the next one bit, go to the next one bit. And so we can actually parse over a bit string telling us where are the comment starts and ends, where the string starts and ends. And we can work that out because yes, on some level we do have to go one by one, but we can do it over a bit string instead of over bytes. And so this can be significantly more efficient. Also, we could do multiple new lines at once. Now if you have long lines, then obviously that won't happen, but yeah, it happens sometimes. So we can do that. That was as far as I got on this particular slide. I had a different set of slides actually, but yeah, so I just want to say the other problem that we address here, So that was this. This is what the actual code looks like. And this is a slightly outdated version of my code. But yeah, we take the or of the unescaped quotes, unescaped apostrophes, and then the comment or line string starts. And then we say, yeah, we have a starting iterator, which is where do we have a new line followed by a non-new line. That's what this says. All the places where there's a new line followed by a non-new line. And then we have starts here where we're doing, this is me using, I put an and not in assembly because the compiler will not figure out how to do and nots properly. That's not even a joke. I've submitted like 8 issues. I'm not even exaggerating. It actually says at the bottom of the file. All or minus iter is what I was talking about. We're doing this subtraction, but instead of -1, we're subtracting multiple positions at once, and then we do the and not. That's this, and not. And this will take us to, this will forward the iterator to the next 1 bit that we see inside of all or, which again tells us where the quotes, apostrophes, comments, and line string starts. And then we take that and we actually produce a bit string where we interleave the answers that we're looking for. So what that means is when we have a quote, we want to find the end quote. And so we interlace the data for the quotes bit string until the new line. As opposed to if it was like an apostrophe, we want to interlace the apostrophe information about where's the next apostrophe. And the reason for that is because if we are inside of a string, we don't want to stop when we see an apostrophe. We don't want to stop when we see a new line unless that's an error condition. And we will stop if there's a new line. But when we see an opening quote, we want to see a closed quote. And so we actually intersplice the quotes based off of, we matched a quote character in this particular position. And so we intersplice the quotes bit string for that range of bits. And then we might intersplice the apostrophes bit string for a different subsection. And then we might intersplice nothing, it'll just be the new lines. And then we can just do it again. We can do a forward iteration, just go forward to the next bit. And if the first one was a quote, we're matching on the next quote, unless again we see a new line, that's an error condition. If we started with an apostrophe, we want to find where's the next apostrophe and just ignore quotes, right? And then yeah, we figure out, okay, where does it end? So we figured out where did it start, where did it end. We have a bit string where we collect this data, and then we set the iter to be this. So we just start again. And I also wrapped it in inline 4. So if we want to unroll it more times, that way it's less likely to branch backwards. It could be more efficient. I tested it on my friend's machine, and it's actually not. So I just leave it at this. And yeah, so anyways, let's kind of get to my last 2 points here. We also want to parse the multi-character symbols. The way that we do that is, I skipped over it. We have get multi-character end positions. And how this works is we call get multi-character masks. And yeah, we produce 3 shuffle vectors. The ith shuffle vector, after looking up textual characters, tells us whether their character is a valid ith character of a multi-character symbol. So how this actually works, this is actually using DFA effectively in vectorized space. And so this will actually produce, what we're saying is, we're using vector shuffles. So what a vector shuffle is where we have a table, and we have a table that's a vector, and then we have some indices. And the shuffle will say, look up each of the indices into the table. But instead of just looking up a single one, we're looking up like 64 at once. Now the lookup table can only be of size 16 for the smallest and fastest one. But we can look up 64 things into a 16-byte lookup table very efficiently. So what I do is I say, okay, well, I'm going to take my characters and I want to look up whether whether a particular character is valid in the first position of a multi-character symbol. So if I have like plus % equals, I want to know that plus is valid in the first position. And so the way that we do that is we're going to be looking it up. Hopefully I can see it right here. I actually haven't looked at this code for a little bit. But yeah, so we take first char data. So what we're actually doing, I think, is we map the values in our chunk. We map each of the characters that can be in a character to 0 through 15, or 1 through 15 actually. We could do either, but the point is we actually hash them. We hash them, and then we make it so that each character is now going to be represented by a 0 through 15 value. So this might be 10, this might be 5, it might be 3. It doesn't matter. But the point is that we assign something that's in the range of a 4-byte or a 16-byte lookup table. So it's going to be 0 through 15, so we can look it up in there. And we have 3 lookup tables, right? One lookup table will tell us, is this character valid in the first position? Another lookup table will tell us, is this valid in the second position? Another lookup table will tell us, is it valid in the third position? We actually do have 4-byte characters that I actually didn't make it support. There's a single 4-byte multi-character symbol. But it's actually not used in any real code. I actually looked it up on GitHub, and I used the code search facility of SourceGraph. And yeah, so that's what we do. So we can look that up, and then basically we want to do an AND on each of these results. So we're saying, is the first character valid in the first position, and the second character is valid in the second position, and the third character is valid in the third position. Okay, but we actually don't want to just know, like, is it valid in the first position, second, and third, because then we could have mismatches. So how do we actually handle that? We have what I call channels. So you might notice how many of these channels there are. There are 8 bits in a byte. So actually each bit that we're looking up corresponds to a channel in this algorithm. So when we're looking up in the 16-byte table, okay, let's imagine we have, let's just say the simplest one, plus %sign equals. We want to know if that's valid. So we look up plus, and that will return 8 bits of information. And it will tell us it is valid to start a sequence that is bar mod, or equal, or self, and these can be followed by these ones. And self is actually a special one where it has to be paired up with itself. So that's saying that plus plus is a valid one. And we do like a special check we do a special AND to make sure that it actually gives us the right thing as opposed to just any random pair. And then we say, okay, now in the second position, we have the %sign. And this isn't aligned, unfortunately, because formatters, I'm using formatter. But % is valid here and nowhere else. And then we say, okay, what about the equal? That's valid here and here. Here, oh yeah, and actually like most of these, it's valid. And then we do an AND. So each bit is going to be a channel. So the first bit will tell us, is it one of these? Is it a plus %sign equal, a plus bar equal, a times bar equal, a times % equal, ditto for minus. And we can group these together because any combination of those things is valid as a multi-character symbol. Ditto for this. So this is the equal one. It's just followed by equal. And so any of these characters followed by an equal, that's fine. Any of these characters followed by themselves, again, we do a special check to verify this. And then we have specific ones where it's a dot ***. This is actually something that's built in as an error. It's kind of interesting. And then yeah, you can have a dash followed by a that symbol, and then an equal followed by that for arrows. And then you can have the shifts with the different variations. And you can have a dot question. And so yeah, again, first bit, second bit, third bit, fourth bit, and yeah, so on. And so the point is that we just line those up, we AND them together, and then if we ANDed 3 ones together, then we know that the first character is in the set, second character is in the set, third character is in the set. And therefore, it matches one of these. And so we can do it that way. So yeah, that's how we do that. And the only other thing I really wanted to talk about, I guess, is, let's go back. So yeah, we get where do the symbols end, and then we actually did have a loop because it's possible that these things could overlap arbitrarily, and you're like, okay, I have a 2-character followed by a 3-character end. And so you might have to work out how that happened. But in real code, it actually wouldn't branch backwards. But I do have a loop where we will check, okay, there's a 2-character end here, a 3-character end here, and these are overlapping sort of more complicated than this. Because actually this we wouldn't need to do anything for. But yeah, so if you passed in like completely awful input, we would handle it properly, and we do have a loop for that. But I didn't make an animation, not that it would work anyways. And then this is for carrying stuff across a chunk. In this code, it's actually not fully completed. But yeah, for this one, we look up the keywords. So how this works, this is actually doing what I said in my last talk. So for each identifier, in order to tell if it's a keyword, first thing we do is we hash it, and then we're going to look it up in a lookup table. So we use a perfect hash function. How it works, we take the first 2 characters, well, let's actually look at a keyword. First 2 characters, last 2 characters, and we take those as a U16, and I think we multiply them, or we XOR them, and we take the length and we shift it to the left by 14. This is all random stuff, but we put it together, and it hashes so that every keyword is different. That's the point. And it's different inside of a U7 space. So there are 128 possibilities in that address space. And in my other code, we actually use Phil Bagwell's pop count trick, where what we're doing is we say in sparse space, we say, okay, at this position there's one, at this position there's one, at some other positions there's one. And then we effectively are able to do a rank operation, if you're familiar with succinct data structures, where there's some number of zeros in between. But we're sort of assigning each of the ones to a condensed address space. So that means that we can have a lookup table that is actually equal or just one greater than the number of keywords that we actually support in our language, which is 49. And so we actually have 49 slots in a table, 16 bytes a piece, obviously overfilling. And we intersplice the length. I showed this in my last talk. We intersplice the length at the end. So we're going to say export, and then we're going to have all 6s until we're done with the 16 bytes. And then for FN, it would be all 2s for 14 bytes. And the reason for that is because we, when we want to look this up, we can intersplice the length for the identifier that we're looking at, and then we can do a single comparison on just that. And so we alleviate the need to have like multiple branches and early outs and all these sorts of things. And I showed the assembly for that last time. I probably could find the God-built again, but yeah. And so we can actually do the hash calculation in parallel. So first thing we do is we say, where do they start, where do they end? We have this from earlier. So the start larger than 1 bit string is saying, where are the starting positions of an identifier that are not the end positions? In other words, is it longer than 1 byte? Because those would be the same if it's 1 byte. And then we say, where does it end? That's where you have an end position that's not the starting position. Okay. And yeah. So then we can take this, we can OR it with itself shift to the left by 1 or shift to the right by 1, depending on whether you want the last 2 characters or the first 2 characters. And we can do a vector compression on this so that we can get all of the first 2 characters of each identifier, all the last 2 characters of each identifier, all at once in parallel. And then we can take these first 2 chars and last 2 chars, and we can do our hash function like we were doing before. We can take the lengths, which also is based off of a compression. I don't use the word compress, but I just say bits to indices because I have a specialized algorithm for my hardware which doesn't have the compression instruction. But yeah, so we And actually, this is one thing I was talking about. You can see how we take the first 32 instead of using the full 64. This is because you can't have 64 identifier starts in a chunk. It wouldn't make sense because there has to be a space between them. You can only have 32. You could also derive this by definition of when you do this, the pop count is at most 32. Ditto with going the other way. And so when we can get the indices here and we get the lengths. And so we take the length and we shift to the left by 14. We XOR it with the first two chars, multiply it by the last two chars. Again, this is like sort of random, but it just works out as a hash function. Then we do a shift right by 8 on the U16 that we ended up with for each of the identifiers. And this ends up giving us a 7-bit hash. In my updated code, what we actually do, we actually look this up in a 128-byte table in SIMD. It's called vperm2. The full instruction is a vperm ITB. That's one form of it. You can also do, actually I'm missing some stuff here. vperm2, something like that. But the point is, you can look up you can look up 64 bytes all at once into a 128-byte lookup table in a single instruction on AVX 512 enabled targets. And so we do that to map the hash into the condensed space of the lookup table, which only has 49 entries, 16 bytes apiece. And then you can see here I do the calculation in SIMD. I actually took this out in my updated code. But the point is, we take each of the pointers, we look them up, and like I said, we intersplice the lengths into the vector. So if we have foo, then it's going to be 3, 3, 3, 3, 3, 3, 3 until the end of the 16 bytes. And fn, it'll be 2, 2, 2, 2, 2, 2, 2. And then we say, are they not equal? The number of truths should be 0. It's just kind of a dumb way to say everything should match. Then we take that as an integer, so either 1 or 0, and we shift that in a particular position, and we're producing 8 bits of information corresponding to the first 8 identifiers, hopefully all of the identifiers that we care about for a chunk, so we don't have to branch back and do it again. So we take this and we map these 8 bits of information into alpha n's larger than 1. And basically what we're doing here is we're doing a vector expansion. And so we're producing a vector that tells us like, okay, we have this vector kind, and we're going to have export, fn, and then this could be like var, let's say, but it's wrong. We're going to know that it's wrong. But this could be var, let's say this is try, and then this is something else that we're going to throw away, a line or something. And then we're doing a vector expand. So we're going to take those things that are written out, where it's going to be export, and then it's going to be fn, and then it's going to be try, right? And we're going to expand it to the position at which it starts, so that it corresponds to these. So export goes here, fn goes here, var goes here, try, what have you. And then we mask out just the things that matched. So this pdep instruction is another, it's a bitwise expansion. And so this will map the 8 bits of matched. It will spread it out into here. And so if this matched, then we'll get a 1. If this doesn't match, we'll get a 0. This does not match a keyword, we'll get a 0. This does not match a keyword, we'll get a 0. And so you can mask it out that way. And then I'm actually not sure what this does. I definitely don't have this in my finished code. We're doing a reverse order on this. Okay, this was me probably experimenting with trying to get it to 0 the lower 8 bits. Oh yeah, I was trying to see if the compiler is going to be smart about constant folding, so I'm defining a constant in a really convoluted way. It's not smart about it, so it doesn't matter. But yeah, the point is we can do a PDEP instruction to lower this. We can zero the lowest 8 bits by having 8 zeros in a PDEP and then have ones that are higher than that. So if you know how PDEP works, right, we're broadcasting a bit string to another one. And so here, if we had 8 zeros that we're broadcasting to each of the ones, then we put a 0 here, 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 and then a few more, I guess. And if we ran out of zeros, right, if the rest of it was just ones, then we'd be mapping ones to the next ones. And so that effectively zeros the lowest 8 1-bits in one instruction. It takes 3 cycles on Zen 3 and up. And yeah, so we do that, we loop back around. This is for all the keywords. Okay, so end of the day, we got the lengths. This is what I was talking about. We have all ends and all starts. This is a bit string that tells us where does every token end, where does every token start. We map it to the indices, we subtract them. And then we've successfully created the kinds, somewhere in here, kinds. And in this version, it's actually compressing it on the ends. In the version that actually works, we're compressing it on the starts. And it makes more sense in actuality that we would do that. But this was in development code when I submitted the issue to LLVM. I don't have the updated code on me, but yeah, and then we advance we write out 64 tokens, and then we advance the place where we're writing to in the buffer by the number of tokens that were actually real data. So we're going to write out 128 bytes, so we're going to over allocate a little bit so that we can do that safely. Technically, you actually could do it safely just using the VP compress B. This is a guarantee. It actually has fault suppression on x86, but there's a hazard on Zen 4 where it will take like 240 cycles if you do a VP compress B straight to memory, and so you actually just want to do it this way because it's safe and it's fast. So you want to over allocate by 128 bytes for the maximum amount that you can actually use. And then, yeah, we have some carry. I just wrote a little helper. We're going to take the uppermost bit of each one so that we can know what was the last byte in the previous chunk, and we can merge that in with the bit strings as we go. And then, yeah, this is the end. We increment the pointer by 64, and we go to the next chunk if there are any more. And yeah, so this implementation, I just want to kind of look at the fruits of my labor on the right here. If let's just go to the top, and I just want to scroll through and we can see how many branches there are. Because this was part of the point. We want to eliminate branching. Branching is really slow. And the reason why is because every time there's a branch mispredict, all the work that the CPU did of feeding instructions through the pipeline, getting them decoded, getting them scheduled, doing register renaming, starting to execute some of them, starting to load up constants. Every time we have a branch mispredict, which is when yeah, for those who don't know, a CPU is a multi-stage pipeline. And when you see a conditional jump instruction that says, if it's true, go execute this code. If it's false, go execute that code. When the CPU first sees that, whether it's true or false has not been computed yet. So what does it do? Well, it will guess based on past history using a branch predictor unit. And if it guesses correctly, then you ended up passing the stuff through the pipeline, and then you say, oh, is it true? Yes, we compute that it's true. Okay, we guessed correctly, therefore the pipeline is filled with the right stuff, therefore we're doing the right thing. But if we guess incorrectly, then the whole pipeline is garbage. You have to throw all of it out. Even if it's a case of a branch backwards. And so we might have been doing work that we're actually about to do again. We can actually throw away work that we already got done when a branch mispredict happens. So anyways, you can see here, this is the start of the loop. We load in 64 bytes from this pointer that's inside of R13. And then we do the initial stuff where we do classifications, like where the new lines, etc. And then we do have a branch here where we say, is there a carriage return followed by a non-new line? And then we got some branch-free code for a while. And then we do have a branch back here. This in source code is, let's try again. This is the loop where we're matching where are the string starts, where are the comment starts, and where do they end. And so this loop here will actually manage that. And yes, it might branch backwards. So we didn't actually get it perfectly branch free. We could theoretically, we could unroll it the maximum number of times that it's possible. to have things inside of a 64-byte chunk if we wanted to. But anyways, let's keep going.
What are you looking at here to determine if it's branched or not?
So anytime you see a conditional jump, so this is saying if it's not equal, jump back up to 507. So this would be a branch backwards if we have this egregious situation I mentioned where we have a bunch of multi-character symbols squished together. We might have to branch backwards and deal with that bit string more than just once. As opposed to most of the time what we want to do is we want to just run this, we check this condition, and this condition always lets us just go to the next one. And the CPU is going to predict that, and the CPU is actually going to be working ahead, and it's going to be decoding and scheduling and loading in the constants and actually working on the next stuff. And every time it guesses wrong, that all goes in the garbage bin, and it says, well, pump the brakes, we have to go back here, do it again. And then even though we literally still have to do this, and a lot of this work would still be valid, it still gets trashed. So yeah, what we want is we want something that doesn't have branches, which is the complete opposite of most tokenizers, which is branch galore, where it's like every single byte, we're gonna branch on it pretty much. And we're gonna do a check, we have multiple instructions to figure out what we're gonna do with it. Whereas here, we're doing it in chunks, we're dealing with large amounts of data at once, 64 at once. And yeah, we don't have branches almost. We do have some let's see. In my final code, this doesn't happen. This is a compiler hazard right here. Oh wait, actually this is for the carry. Let's ignore that for now. And then, what else we got? This produces the kinds. And yeah, you can see we're doing some broadcasts, we're doing some shuffles. This corresponds to the, this is for the hashing. And then yeah, this is the branch backward for if we need to check more than 8 identifiers to see if it's a keyword. And yeah, we unrolled it by a factor of 8. And so we're going to be loading in 8 16-byte chunks independently. So we can't do that 100% like in SIMD, right? And yeah, you can see the VP expand B that I was talking about. And then yeah, this is the end right here. We interlace the data and we write it out to memory. And then this is something to check for if it goes across the chunk. And then we do a bunch of stuff for stuff that can go across chunks. And then we check, do we have another 64-byte chunk? And we branch back to the top. So we mostly eliminated branches. They still exist, obviously. And it's possible to branch backwards. But in practice, we want to be able to do this without branching. So yeah, I'll tell you how fast this is. So I mentioned that for my old tokenizer I presented at the beginning of this year, the old numbers were this, where we got, this was just reading in files, 250 megabytes per second on the mainline tokenizer that Zig has, and then my version about 750 megabytes. This would be a little bit lower now because the UTF-8 validator is turned on. And theirs would be a lot higher, a lot better now. They actually, on my machine for this particular test bench, this was like 160 milliseconds. So whatever that translates to in megabytes per second, you'd have to do the math, unfortunately. But theirs got a lot faster again, for those who missed it, because of the labeled continue. And so before, LLVM is really bad at a lot of things, okay? And one of them is when you have a state machine, when you have a switch statement inside of a while loop, and you're like, okay, I'm switching on variable x. I'm going to set x to 1. That means we should go to the switch case that corresponds to 1 when we loop back around. And we're looping back around immediately after setting x to 1. And so LLVM will literally put in your code, set register to 1, check if it's 1. If it's 1, jump to the location. Instead of just saying, jump to the location. And if it was just once, it wouldn't be a big deal. But when it's for your whole program, that really bloats it. And so it got way faster this year for this. And yeah, so on my Zen 3 machine, for the updated tokenizer, this new one that I produced in the last 2 weeks here. I did some of the operator stuff earlier, but how fast that was, I have the numbers on my phone here. On my Zen 3 machine, we got, we got about, let me look at the numbers. For the original tokenizer, it was like 300 to 400. I have the exact number for the thing I care about. It was like 300 to 400 for the mainline implementation. For my old tokenizer that I presented at the beginning of this year, we got, it was about 750 again. Might be slightly less. For my new one, on my machine, we got 500 megabytes per second for the compression tokenizer. It was actually slower than this version. Now, this actually vindicates the fact, as I said earlier, I produced this older tokenizer first because I knew it would be good across architectures, across platforms, where we do not have the certain facilities that I optimized for here. But I have a friend who has a Zen 4 machine, and we tested it out. I actually have the numbers that he texted to me. And my new algorithm, okay, can I flip this around? Can I do that?
Is there knobs or something?
Just 1 or 2 turns, come on now.
Yeah,
You
can you,
don't have to do it a million. Or maybe you do, never mind, I lied. I thought it was just 1 or 20. Is there a latch?
At the bottom, right here. Somehow.
Yeah.
Pull at the bottom. There's a
There you go.
bottom.
Okay.
Put your hand down.
Uh,
Put your hand down.
Can we do it the other way
Underneath the
so we
rail.
don't
Put your hand down.
pull it down?
There you go. Beautiful. So, the legacy tokenizer on my friend's Zen 4 machine is a little bit faster than mine, obviously, because it's a faster computer in general. It took, it could do 450.58 megabytes per second for the legacy. Let's say V1, the tokenizer I presented at the beginning of this year where we eliminated the branching on each individual continuation character. We got 832.94 megabytes per second. My new version,
Right big.
sorry,
No, you leave it. Continue. I'm
my
just
new
saying.
version, V2, what I just came up with,
That's good. Yeah, if I didn't have my glasses on, I can't read that one, but I can read this one.
it is 1358.36 megabytes per second. That's 1.3 gigabytes per second. So we finally broke the gigabyte barrier on Zen 4. Okay, this is Zen 4. Now, I mentioned before, Zen 4 has a double pumped implementation of AVX 512, and that means like in real world benchmarks where we test AVX 512 code, Zen 5 is 2 times faster at AVX 512. So I believe it is 100% reasonable to predict this will legitimately double. It might even go higher because it's also 20% faster at integer arithmetic stuff. And we also, there's a couple more advantages to it as well. Like there's advantages from the perspective of individual instructions are faster. So VP compress B, something my code hinges on Zen 4, 9 cycles, the version we care about. On Zen 5, 5 cycles. Almost a double right there. But in terms of how many operations we can start every cycle, we can start a lot more. For the simple ones, we can start 4 per cycle. For some of the more crazy ones, like looking up 64 bytes into a 128 byte lookup table, we can actually start 2 per cycle.
So when is Intel going to get someone on the LLVM team? I mean, like, what's the purpose of AMD and Intel making these processors so great if there's nothing that can use it?
Well, that's another thing I wanted to point out, actually. So this number right here should be higher, right? What did I point out in the code? The assembly sucks, part of it, right? It's like, okay, we moved from a general purpose to K1, we moved K1 to the stack, and then immediately moved from the stack into K2. Why did we do that? There's no reason to do that.
Well, I mean, there is, but
There isn't.
well, no, there is from the perspective of if you think about it as code, not as assembly, but if you think about it as code, somebody's writing the code to generate that because somebody had to write the code to generate it, right? You know?
Yeah.
So it's you know, if they had a machine learning algorithm that produced a bunch of random stuff and then tested it, I don't know.
Well, here's the.
But I know how that problem with the switch statement occurred. I know because of a jerk like me. That's why it exists.
I guess. I don't know.
Clean code, brother.
Maybe I should blame clean code. Yeah, all those virtual function calls, right? That's the problem. But yeah, so this is 3 times faster than this, and I would rightfully expect it to be 6 times faster on Zen 5. And yeah, Zen 6 is going to be better than Zen 5 in the sense that for Zen 5, the latency of our 1-cycle SIMD operations was regressed to 2 cycles. But on Zen, because there's a hazard. And then, yeah, on Zen 6, it should be reduced back to 1 cycle. So going into the future, this implementation, this is what I showed with the case Imidar video, where it's like, if we optimize for the computers of the future that actually have compression and expansion facilities, where we can do a vector compression, we can do vector expansion, and we can chain these together with bit manipulation, we can actually operate on something almost entirely in parallel and get the highest throughput that we've ever seen for a tokenizer, for a real programming language, at least on the CPU. A few caveats there. But yeah, so this was something that I actually saw yesterday. I actually just measured this yesterday on my friend's computer. So there's still more work that I could do with this. Still some tuning to do. And yeah, but I'll release it so people can look at the final code in a few days. And yeah, that's what I came up with. There's going to be a parser stuff. Maybe I won't go over it tonight. But yeah, I have a different idea than how people normally do that as well. So yeah, I think it's probably pretty late. So 9:15. I don't know. I could just say what the data structure is if anyone wants to hear it, or you guys can leave. So I won't be offended either way.
What's the structure?
I have evil plans for the phase after the tokenizer, the parser, and I could just say what it is. I don't have a slide for that or anything. Not that I had slides for the rest of it. But okay, so what we do for the parser, since you guys did not walk up and leave, now's your opportunity. For a parser, right, we have A plus B times C divided by D. And we can have minus E. And one of the things that we want to do for parsing is we want to figure out order of operations. So you've probably seen abstract syntax tree before, where we want to sort of like, lift these up, and we want to figure out like what's going to happen first in order of operations, and then this, and then this, and then this. And so we can encode it as a tree. We put times at the top, and we're going to do B and C. And hold on, I'm probably doing this wrong.
You're at a leaf node right now.
Yeah, this has to be at the bottom. So I should probably draw it a little lower. Thank you. B and C times. And then that's going to be divided with D. Okay. Let's do the division symbol. Divided with D. And then added to A. Okay. and then we subtract that with E. E is going to be somewhere over here. Okay? So this is part of what an abstract syntax tree is for. And I'm sure you guys have seen this before. It's just, you have a tree-like representation of the code, and it helps you do checks on it to make sure that it's syntactically and semantically valid, mostly semantically. And then we encode the order of operations. So when you have a tree like this, you can do a depth-first traversal. And if you look at the post order, that will be the proper order of operations. So depth-first traversal is where we go as far left as we can, and then we come up and we go as far right, or we go right and then as far left as we can. And yeah, hopefully you guys have seen that before. And yeah, so there's 3 orders in which you can do a depth-first traversal. There's pre-order, in-order, and post-order. So it's typically visualized like this, where we kind of like draw the line of when we're seeing things. And basically, pre-order is when, like, the first time we see it. So we would see plus, A, and then we see division, and we see star, B, and then we see C, and then we see D, and E. Okay. In order is when we're like in the middle. So it's this A, this plus, and then B, star, C, division, D, minus E. That's in order. And this kind of tells you what order it was in the file. This. For a binary operator, this is the case. When it's a like unary prefix or postfix operator, then obviously the prefix will tell you the order that's in the file, and postfix will tell you the order it's in for a post operator. And then, okay, so what did I say? I said post order, that's the last time you see it. So when we're like on this far right end. So you see A, and then you see B, you see A, and then you see B, and then you see C, and then you see star. And then you see D, and then you see division, and then you see plus, and then you see E, and then you see minus. This is post order. Okay. And yeah, and pre-order. Pre-order was plus A, division, times B, C, D, E. And I missed the minus at the top. Minus goes over here. Pre-order, post-order. Okay, so when you have a tree, the post order tells you the order of operations effectively. So the times comes first, division, and then the plus and the minus, which is how I do it right here. Okay. You can operate on either of these using a typical stack-based algorithm. I had to do this for an interview one time actually, where it's like, okay, I see minus, so the next 2 operands I see are going to be minus, except you see an operator. So now we're looking for the next 2 on this, and we matched 1. So we have 1 that's being added, and then we have division. We're looking for the next 2 operands for that. And we see times, we're looking for the next 2 operands for that. Okay, we actually matched 2 right here. So this now becomes an operand to this. And then we look for the next operand, which is D. So we're doing the result of the times and the D, which makes sense. And then we did a division. That gets moved up to the plus with the A, which is also what we see, okay? And then we grab the E and we do a subtraction, right? So this is just different ways of writing it. You can use a simple stack-based algorithm to evaluate it either way. Now, the different orderings are going to be advantageous for different phases. And yeah, we can do really nice checking on a pre-ordering of the tree. So when it comes to something like, we have a statement node. So if can I actually just bring up an abstract syntax tree diagram? I have a website in mind, if we're still able to be connected. You can see what this looks like. Here's a TypeScript AST. If I say A equals B plus C times D divided by E, okay? You can see at the top level we have this expression statement. This just encapsulates everything. And yeah, we have a binary expression, which is the r equals at the top. And then on the right-hand side, we have this. Sorry, where's my A? My A is right here. So yeah, the binary expression. So yeah, this binary expression represents this equals. And then we have A on the left, this other expression on the right. And so you have this tree-like representation. And this is good for validation, right? Because this enables us to do checks that would be sort of difficult to do while we're producing the tree, which is, you know, for example, we can do a check where we say, okay, if we're looking at an assignment, that would be the uppermost node. You couldn't write code like that while we're going one by one over the tokens. So you say, okay, if we're looking at an assignment, look at the left-hand side. The left-hand side should be a pointer dereference, or it should be at field in Zig, or it should be, you know, just like the name of an identifier, or maybe some chain of A.B.C, or yeah, it has to be one of these things. So you can effectively match, like, okay, it needs to have this postfix operator, or it could be this other thing. And because these things are rearranged, it makes it very easy to do these sort of checks. Whereas, you know, you could check it when you're parsing, but this is how it's done a lot of times, because it's easier to check it when it's in a nicer format, where you can just check, like, I'm looking at this, I say, what's on the left? And that's a lot easier than saying, like, that's a lot easier than saying, like, matching it incrementally, where you're like, okay, I've seen a thing, if I see an equals next, this would have been valid. You could do that, but you just have to track more state, and you maybe more stack space as well. And so this is the way that parsing works a lot of the time. Okay, so Chandler Carruth has a different idea for how this should be done. What he actually does is produces these in post order and lets the next phase consume it directly. This is actually in contrast to most other compilers. Although someone in the peanut gallery, when he gave the talk, said that Nicholas Worth's compilers, like for Forth, I guess, was listed as an example. Their compiler would do this. But most people are consuming a tree in pre-order. It actually looks like this. So we have this at the top, and we have our left and right, as opposed to a post order where it's going to be a little bit harder to deal with. And I'm biased against this because for my tokens, what was the structure? We had a kind and a length. Each one of these is a U8. We can actually represent a abstract syntax tree. This is actually a replacement for it. It's not exactly the same. But we could represent a quote-unquote, scare quotes, abstract syntax tree as just taking the individual tokens and reordering them. And we don't actually need any pointers to represent it. We don't actually need the start index of anything. And the reason why is because, for one, when it comes to these nodes in particular, because I drew it, each of these nodes have a fixed arity. That means there is precisely 2 children, which is what we take advantage of when we are evaluating them with a stack-based algorithm. That's number one. And we can extend this to anything that we want. We can say, okay, an assignment has a left child and a right child. And in fact, for those of you who have dealt with trees a lot, you might know that there's something called the LCRS form, a left child, right sibling. And you can reduce any tree to having only a left and a right. And yeah, so you can actually model the abstract syntax tree as simply a reordering of the token buffer. So you take the 2-byte tokens and you just change the order. That's all we're doing. And what we're effectively computing is we're computing what is the order of operations. That's part of what we're encoding. But we're also encoding like what's the pre-ordering, which is effectively just a linearization of this. Okay? Now, the way that we can actually produce this, the way that's typically done, is we use something called a parser or a top-down parser. This is how almost all compilers I've ever seen operate like this. You could use an auto-generated thing, and there are some more esoteric kinds of parsers. There are like a million different kinds of parsers, actually. but most people just use a handwritten top-down because it's easiest. Typically, there's better error handling associated with these as well, because you can just stick the error where you want it, as opposed to like auto-generated code. It's not really what you can do. So okay, so we do the syntactic checking, we do the order of operation encoding. Okay, the other problem. How can we get by with just a length? Just a kind and just a length. We're reordering the token buffer. How do we know where we are? Well, when we see the post order buffer, the problem with this is after the first character, we actually would have no idea where we are using this length trick, where we just have a pointer in the file and we increment the length. But when it comes to pre-order, right, we're traversing this conceptually. And so we actually can deal with this, right? If you remember how you do a DFS for node, you can say if, right, first we'll have the check, if node is null, return. Otherwise, DFS node.left, and then DFS node.right. Right? So this is the typical way that DFS is done. Pre-order is anything that happens right here. In order is anything that happens right here. Post order is anything that happens right here. We can actually do any of those simultaneously, however much we want. That means that for a binary operator, which is very easy to tell, this is always binary. And if we have a unary minus, for example, we assign that a different kind. So and we can check this based off of context when we're going over the tokens one by one, where we say, okay, if we're in the context, like let's say we had a plus, and then we see a minus. The context is we saw a binary symbol, therefore we can't have another binary. But if we do see something that could be a unary, that's valid, we can reclassify this kind as a unary minus. Therefore the arity is fixed to 1. Therefore we didn't violate the principle over here that we're relying on. And so in the way that I print it in my code, it will like print out unary minus, and so you know you're only grabbing 1. So, okay, so for in-order stuff, like all of these, you add the length right here to the cursor. For post-order operators, like the dot asterisk, you add it right here. For a pre-order, you add it right here. And how do you go left? Add 1. How do you go right? Also add 1 in context, because you're gonna get the position back from here and just like you're going one by one through here. You're just going straight through. No pointers. Now this also regresses the option of like, oh, I don't want to look at this part of the tree. Oh, I don't want to look at this. We can't do pruning. We can't do random access. But when I was writing that transpiler for TypeScript, we never, ever, ever did that. We always looked at the full tree. Like, we want to look at your code in a compiler, right? We're not, like, discarding your code. And then we always did it in the same order every time. So you can do a linearization like this. Okay? So that's number 1. This is like the end goal. So how do we get there? Like I said, how this is typically done is with something called a parser, if you're familiar. It's equivalent to, there's a simplified algorithm, which was one of the earliest algorithms in computer science, actually, by Dijkstra, called shunting yard. I actually learned about this in a discrete math class in college. And yeah, it's basically like you have 2 stacks. Donald Knuth has a version with 1 stack in his Art of Computer Programming book. And yeah, you're basically just working out the precedence, and you're pushing and popping from that. Okay, but the actual thing here, the actual observation that I see is we can produce this tree without resorting to tree-like tactics. Okay, so let me put it this way. For a prat parser and for shunting yard, for any of these algorithms, for a stack-based algorithm, it's impossible to get pre-order without something akin to linking up a linked list or concatenation. It's always produced in post order. The nodes are, like if you printed out the nodes when we made them, it would be post order. And in order to get them in pre-order, what you have to do is you have to return the pointer up so you can link it up in pre-order. This is like a linked list or like a tree. Or you would do concatenation. If you were like in JavaScript and you're like, I don't care about a real language, I'm just going to add strings together and it will concatenate them using ropes. Okay. So yeah, does anyone know what a rope is? A rope is like a string data structure, but instead of just the naive version where we have an array of 10, we have an array of 16, let's allocate 26 and copy them both in separately. This is like the naive way of doing array concatenation. With ropes, it's like a tree-based structure or like a linked list. And so it's, we're not going to allocate new buffers for absolutely every single thing. And so we try to get like logarithmic insertions and stuff for ropes. So my idea is actually not entirely dissimilar from the idea of ropes. So what we do is we do naive concatenation for arrays of a constant size. So let's say we have 32 bytes of tokens. That can hold 16. And then different in terms of constructing the tree, at least not that I'm saying right now. And yeah, so we can have 32 bytes. Anything that's within a constant size, we can do the naive array concatenation. Anything that's like larger, where we say maybe it doesn't make sense to bloat the binary with a ton of these objects in our cache, then we can have a pointer or a 32-bit index in an array where we say, okay, this one points to the other one. But at the end, I still want to linearize this structure. So I'm going to follow all the pointers, and I'm going to make it completely flat. Now this can still be, this actually isn't as bad as producing a full tree because it's more like we have the data in our cache and we're sort of juggling it. Okay, we're kind of moving it between these buffers, and so we never actually have a structure that is like completely this kind of tree, even though we are putting together these pointers in sort of a linked list fashion with this. Okay, so the other thing to notice about this algo, that I don't know if anyone has taken advantage of this in the past, I highly doubt it, but one thing that you'll notice, if you look at the pre-order or the post-order, the thing that we're really doing here is we're reordering the operators, effectively. The operands are always in the same order. A, B, C, D, E. A, B, C, D, E. This is always the case, always. Okay, so that means that when we are doing the algorithm to produce the pre-order linearization of an abstract syntax tree, we don't actually have to involve the operands almost at all. Because it wouldn't make sense to say, oh, this times is attached to this BC. This division is attached to this D and this star. None of that matters. All that we actually want is we want to know minus, plus, division, times. That's it for this case. We want this. And A, B, C, D, they're always in the same order. Now, you do have to know where an operand goes. But you don't have to track which one when you're computing it. That's the point. So we can have a bit string that tells us how to intersperse the operands and the operators. So we might have something that looks like this, just random bits. And in the data structure, the intermediate data structure here, I have 16 tokens. These are all operators. Minus, plus, division, and star. And then I have A, B, C, D, and E. I can intersperse these based off the bit string now. There's an instruction for this. VP expand D. So what this does, takes in a vector, let's say this, and it takes in a bit string, let's say this. And it will spread out the elements in the vector so that we're moving the data elements to the positions where there's ones. So effectively, we're adding padding where there's zeros. Okay, so this would be spread out. And then we're going to have a space. And we're going to have a plus. And then we're going to have the division. And then we're going to have a space. And then we have the star. Now, I just put this bit string here randomly. But yeah, we have these spaces. We do a not. We invert all the bits. We do another VP expand on this, which will put an A in here, a B in here, a C after that, and yeah, I chose the bit string arbitrarily, so it's not the correct one for this. But this is the point. With a VP expand B, we can put the operators in the right spot. Another VP expand B, we put the operands in the right spot, and we needed a not. And actually, this will take the second VP expand will take the first one as a fallback. So it will actually combine it automatically. So actually, in just 3 instructions, 2 of these and a not, we can interlace 2 vectors according to a bit string. So that means that genuinely we can do all of our operator shuffling stuff where we figure out what the order of operations are. We can do that without actually looking at the operands. All we need to know is where they are. And so we could have a bit string that tells us that. And yeah, this effectively cuts the amount of memory we have to look at in half for this algorithm. So
would you have a bit string for post and pre? Or just
we actually don't produce post.
Just pre.
Just pre. And post is easier because you don't need to do any of this. Post is the default. Post is what you can produce just by doing the stack-based stuff. But if we put it in pre-order, one, it's nicer for checking.
Right.
And it's also nicer for this. We can have tokens that are just a kind and a length. And our abstract syntax tree replacement is actually just a reordering of that. So we're not keeping track of where these things start. But we can reconstruct that by having a cursor into the file. And then we can add the pre-order lengths in here, the in-order lengths in here, and the post-order lengths in here, meaning that the abstract syntax tree is now equivalent in size to the token buffer. It is simply reordered, and we can actually, we don't need the token buffer anymore because we can perfectly reproduce it by doing this, right? So this solves a problem that a lot of people have theorized about solving because one, abstract syntax trees are typically not 2 bytes per node. Chandler Carruth in his talk on optimizing the compiler for modern times or something like that, he said that in Clang, he typically sees an abstract syntax tree that is 50 times the size of the source file that it came from. That's not including imports, that's not from the standard library. That's just like the code that you wrote times 50. That's how much memory it takes. And he said it's not uncommon to see a multiple of 100. This strategy actually allows it to be a reduction. So it would be the same as before that I had when I said that for source files that total 59 megabytes, 18.5 megabytes is what we get for the tokens. And because the abstract syntax tree is merely a reordering, abstract syntax tree, it's merely a reordering, that means that the abstract syntax tree is actually a reduction on the source file. So that means that now it actually can be beneficial to serialize this to disk. I saw Andrew Kelly on a podcast recently say it's not worth it, and you may as well just reproduce the abstract syntax tree every time because it's too large and yeah, it's not worth it. This would be a lot smaller than your source file, multiple times smaller. And so this actually unlocks a whole category of optimizations that was not possible before by using this sort of strategy. I did do one other thing on top of this, which is I actually tried to shove a whole Zig program inside of a shunting yard algorithm. Obviously, it has to be extended, and you have to check errors inside of that. But what's interesting about that, as opposed to using a top-down parser, is that it's like 100 lines of code. And it does everything. But that means that you have to say that everything is either an operator or operand. So if you have const, you're like, okay, that is a prefix operator. There you go. It's a thing that comes before a thing. What is inline and fn? Those are inline prefix operators. Everything is an operator or an operand. So yeah, I also did that. Although this strategy can be used independently of that kind of idea. So you could use this with a top-down parser or a parser. And you can use this technique where you store a bit string in here, as well as the pointer to the next, and then you store a constant amount of tokens, and these are just going to be operator tokens, and you can intersperse the operands after as a post-processing step. And yeah, so hopefully we get numbers like this for subsequent phases of the compiler as well. But this, I hope, yeah, this will enable a whole category of optimizations that people have not been able to crack in the past. So I'm really excited about this. And I'm really excited about the stuff I did with the tokenizer too, because going forward into the future, a compression-based tokenizer, like it's going to be twice as fast on Zen 5 than this, at least. And if we get LVM fixed, then we can maybe do better than that a little bit. So, do you have a question?
Can I ask a naive question?
Go ahead.
How does it enable optimizations?
How does what?
This
Oh, yeah.
compressed format.
So what I was talking about, Andrew Kelly said in the podcast that they don't bother serializing an abstract syntax tree to disk. So when it comes to incremental compilation, what we would prefer to do in an ideal world is we do the minimum amount of work possible to say, okay, you changed one character in your file. We don't want to like just do all the work all over again, which is how a lot of things work. With incremental compilation, we want to say, what's the smallest amount of work we could possibly do to get to a finished binary based off of the work that we did in the past? And so with the abstract syntax tree, for Zig, they determined it's not worth it to serialize it to disk because it's too large. You may as well just produce it again because like the speed of trying to deal with it is just...
So there's a performance benefit because you just load the serialized format. But I thought you were talking about like compiler optimizations on rolling loops and and stuff like that.
Yeah.
Maybe I misunderstood.
In terms of unrolling loops, yeah, I mean that would
That's smaller.
Everything is smaller, yeah.
You use it like an AST.
You use it like a tree, yeah.
So everything that you would do.
But you have to touch every single node and you can't prune anything. But we never do. We never do, right? So, I mean, maybe there's some applications where they're like, oh, what we really want to do is we want to show you an abbreviated form of your file. So here's like all the function definitions and the constants in the top level. And you could do that on a tree by just looking at the bottom stuff. So you couldn't do like that specific thing, but to be honest, that's not an actual optimization anyways. If you actually looked at the memory footprint and the cost of doing that, if you actually just went over the whole
like
tree,
for an editor, so you want
yeah,
to
for
do
an
that,
editor, yeah.
But for an actual compiler.
Yeah. Yeah. So this represents several orders of magnitude better than like Clang, which they have to deal with C++, so it's not like I fault them for that, but actually like 8 times better than the memory footprint for Zig. When I looked up, like I calculated for my test bench, how big is their abstract syntax tree? And yeah, for us it's just the tokens reordered, and we're actually like increasing the amount of information by reordering it. And again, we can also get that back whenever we want by doing this. So, yeah.
It's so sad you can make the tokenizer and parser so fast and then you have to hand it off to LLVM.
Yeah, but we are working on that with Zig. We're working on our own self-hosted backends, working on our own optimization passes. And yeah, if I actually get in there and work on the vector backend, I'll fix all of the things that I hate about LLVM. So yeah, I'll put all the different routines I can think of and all the different combinations. Yeah, so yeah, this is what I've been thinking about recently.
Can I ask another question?
Yeah.
Nothing to do with anything. You mentioned RISC-V on your GitHub.
Yeah.
But I'm sorry, I'm late. I didn't see what it said about RISC-V. I'm just wondering, like, what vector stuff you've done on RISC-V. It seemed like
Yeah.
it looked like you were doing some optimization on RISC-V. I didn't know if you had, like, the latest instruction set or if it was the outdated one that
Sure.
was all broken.
So on RISC-V, the single board computer that I bought first did not have vector facilities or bit manipulation. And in my previous talk, I talked about how we can still do the older tokenizer that I did, which I think you missed, but the older tokenizer, this one here, we actually still got 2.5x speed up, which on my Zen 3 machine, we got a 2.75x speed up for this technique. And this technique for the tokenizer was just, for every 64-byte chunk, produce 3 bit strings that will allow us to jump over the continuation character. So we have 1 bit string that tells us where the alphanumeric underscore, 1 bit string that tells us where the white space, 1 bit string that tells us where the new lines. And so depending on what token we see based off the first character, we can, if it's a comment, we can jump to the next new line. If it's a keyword or identifier or number, we can jump to the end of that. And yeah, so for that one didn't have vector or bit manipulation facilities, and I showed that data level parallelism is it's a sort of universal truth on this. Now, I actually did buy a machine that has the new 1.0 ratified vector support for RISC-V. I actually have not turned it on yet. But I can tell you this algorithm here, we do have a vector compress on RISC-V. It's called vcompress. And we do have, we can do a vector expansion in 2 instructions. Yeah, you guys can all leave. I'm just answering his question. viota plus vrgather. We can do an expansion, 2 instructions. viota is actually a prefix sum instruction. So it will actually just add up some number of things. And so if we have a 1 corresponding to each thing, we could find the prefix sum of that. And then that would tell us, we can pass it into a vector shuffle, vrgather, and then that will spread out the data as we want it.
We're gonna need to wrap it up because the door's gotta get
Oh,
locked.
okay, yeah.
It is close to 10.
Last thing I'll say, we don't have pdep and pext on RISC-V. pdep and pext are the bit level expansion and compression. We don't have those. And that kind of sucks. We don't strictly need them, but they're really nice to have. We could get away without, but it would just be slightly more inefficient. Also, something I hate, just pet peeve of mine, x86 and RISC-V, they don't have bit reverse. That's really annoying to me. ARM has it, and in fact, that's the canonical way they do count trailing 0, because they don't have a count trailing 0, but they have a bit reverse and a count leading 0. So, anyways, the thing that I use the bit reverse for is just that trick where we did a subtraction and then and not to move the iterators forward. With a bit reverse, we can go backward. There you go. So, anyways, we should finish. Let people go. He's giving me the look.
I'm giving you the look.
So,
I have not had to give
that's
anyone
it.
the look in the last
All right.
3 years. But I am giving you the look. Yes, thank you. Thank you very much. This is great.
This is really fantastic.
And there's a number of people that joined in online too, so I'm not going to wait for them to say thank you, but I'm sure they say
Yeah.
thank you.